So, we were learning how to obtain mathematical models of various types of systems, and we have seen that there are some phenomenological models which are obtained, the phenomenological models. Which can be obtained by a few different means, one of them being the dimensional consistency method. And we have seen that also we can derive models starting from the first principles, and then the models that we arrive are not phenomenological models. So, there are various types of mathematical models that we obtain. Today, let me give an example of a modeling procedure that sort of follows from common sense. It proceeds from common sense. It concerns how wild populations of different species vary with time. Now, field biologists have observed how this population, the number of specific individuals in a population, in a species, they count them and talk about the density of that particular species. And the field biologists have for a long time noticed that the populations oscillate. Why do they oscillate? Why do not they reach an equilibrium and stay there? For example, if there is a predator species and a prey species like lion and wild beast, tiger and say deer, something like that, then for some time the number of deer will increase and the number of tiger will decrease, and then after some time again the number of tiger will increase, the number of deer will decrease, and so on and so forth. But we do not really observe that they are reaching, both of them reaching some equilibrium, so that the number of deer that are produced by normal reproduction, exactly the same number is eaten by the tigers, then it would reach more or less a equilibrium, but that never happens. Why? It was a question for a long time, and the riddle was solved only when we could obtain a mathematical model. So, let me just illustrate how such mathematical models are made. Imagine that the number of individual animals in a population, say the prey population, is denoted by x. So, the number of prey is denoted by x, and the number of predators is denoted by y. Normally, the x and y would be whole numbers, but for the sake of simplicity, let us assume that they are continuous variables. If the number is large, then it does not really cause much difference. So, that we can when we try to find out how they change with time, we can talk in terms of derivatives. So, we assume x and y to be continuous variables. That is a bit of approximation, but nevertheless that is acceptable approximation, so long as the number is large. So, now the question is, how would the number change with time? So, our question concerns the character of dx, dt and dy dt, and that is what we try to find out. Now, the logic would be that in that forest, if there is no predator, then how will the prey behave? It follows from common sense that the number will increase, number of prey will increase, and it will increase in proportion to the number that is already present. So, if a large number is present, then it will increase more. If a small number is present, it will increase less, quite natural. So, it is the dx dt will be dependent on a function of x, a linear function of x. So, let us call it a x. That is a reasonably good approximation that follows from common sense. Now, you consider that the forest also has prey species, predator species. Predator species, if predators are present, then that will reduce the number, and so there will be a negative term, it will introduce a negative term, and that negative term will be dependent on the number of times the deer meet the tiger. It will be proportional to the number of times the deer meet the tiger, and the number of times deer meet the tiger can be sort of approximated by a simple product of x and y. So, it will be dependent on x, y. So, if the number of predators are small, then it will have very small number of interaction between the predator and prey. If the number of prey small number of interaction. If the number of predator is small, then also there will be small number of interaction. If both are small number, but if they are both in large number, then there will be a large number of interactions. And so, you can see that this is a reasonably good estimate of the number of times they meet each other in the wild environment. And of course, it will be dependent, it will be proportional to x, y. So, there has to be a proportionality constant upfront. So, that will be let us add in the first approximation following from common sense, proceeding from common sense, that will be the equation for x. What will be the corresponding equation for y? dy dt. The corresponding equation for y will have the same, will proceed by the same kind of logic. Suppose the forest only has the predators and no prey. Obviously, the predators will die out, and how will their number decrease? Their number will decrease in proportion to their existing number. So, and it will be decreasing. So, it will be a minus quantity, negative quantity, and it will decrease in proportion to the present number. And so, let us put a proportionality constant C. Now, you put in the prey species. The forest has the prey species, and so it will have a positive number, because if the existence of prey will make dy dt a positive number, it will increase, and so it will have a positive value, and that also will depend on the number of times the predators meet the prey. And so, as we have seen that it is represented by the multiplication, the product x y. So, here also it will be a plus x y, but a different proportionality constant. So, in the first go, that will be the model of the system, and such a very simple model is called a Lotka-Volterra model. Now, such models are actually quite useful in answering the question that we started with asking. We asked, why do they oscillate? Now, if we have a model like this, you can explore the behavior of the model, or in other words, how would x and y vary if this model were correct. And for that purpose, the first thing that one does is to obtain what are known as the equilibrium points. So, in this model, what are the equilibrium points? Now, equilibrium points are those where if the number of x, number of y are there, then they will not change, which means that such values of x and y, so that dx dt will not be changing, that will be 0 and dy dt will be 0. So, in order to obtain the equilibrium points, we are trying to figure out why we do not see equilibrium points in nature. So, we simply obtain the equilibrium points. So, the first equation, if dx dt is put equal to 0, you get ax minus bxy is equal to 0, and this immediately gives x times x can come common, a minus by equal to 0, and the second equation gives minus cy plus dxy equal to 0, and this gives y comes common, and now minus c plus dx equal to 0. Now, this being 0 can come from two possibilities, x being 0 or this being 0. So, one possibility x equal to 0, and the other possibility is a minus by equal to 0, or y is equal to rather I will write here y is equal to a by p, and this gives either y is equal to 0. So, y is equal to 0 or x equal to c by d. So, there are, we can see that there are two equilibrium points, one is x equal to 0, y equal to 0, the other is this x equal to c by d and y is equal to a by b. We can write these two equilibrium points as 0, 0 and c by d, a by b. So, these are the equilibrium points. Now, 0, 0 is a trivial equilibrium point, which means that there is neither a predator nor a prey in the forest. So, obviously, if there is no predator nor prey, no animal in the forest, we do not expect that to change. So, this is a trivial equilibrium point and not of our interest. Of our interest is this, because if it stabilized, it would have stabilized at this point. That is the only point at which it can stabilize normally an equilibrium, possible equilibrium point. But why does it stabilize in this equilibrium point? That is the next question. Okay. In order to explore that question, we notice that these equations that we have obtained are nonlinear equations, because there are x y terms. X y is a nonlinear function, and therefore, there is this is a nonlinear equation, and if you have nonlinear equation, then the behavior in different parts of the space will be different. So, let me plot it once. Now, you can see that this point is an equilibrium point, but is a trivial equilibrium point, not of our interest, but there is another equilibrium point somewhere here, which is whose x coordinate is c by d and whose y coordinate is a by b. So, if it did stabilize, then it would be, so x, this is x, this is y. Then the prey population would stabilize at the value C by D, and the predator population should stabilize at the value A by B. But our question then is, why does not it stabilize? Now, in order to answer that question, we explore the neighborhood of this point. So, the behavior of a nonlinear system can be different in different parts of this x y space, but we can easily explore the behavior in the neighborhood of this, and in the neighborhood of this equilibrium point we can locally linearize the behavior. So, we can locally linearize the behavior around this equilibrium point, and if we do so, then we might obtain something of interest. Why? If you start from a point something like this, that means x value this and y value that, why does not it converge onto the equilibrium point? How do you locally linearize this? Well, local linearizations are done by the method of Jacobian matrix. Let me draw a line here. The method of Jacobian matrix, where the Jacobian matrix J, let us call it J, is a matrix. Okay, let me give the names. Let this be, let me also erase this. Let this be one function of x and y, and let this be another function of x and y. So, f1 is ax minus bxy and f2 is minus cx plus dxy. So, let us call them these functions. Then the Jacobian matrix is the derivative of f1 with respect to x, derivative of f1 with respect to y, the derivative of f2 with respect to x, and the derivative of f2 with respect to y. Sorry. Now, this matrix can be calculated for this particular set of things, and it will be, you can easily see what it will be. The first function, when taken derivative with respect to x, it becomes a minus b x. So, a minus b x, no, b y, a minus b y, a minus b y. This first function, when differentiated with respect to y, this disappears, it becomes just minus b x, minus b x. This function f 2, when you take a derivative with respect to x, this disappears and this becomes just plus dy. So, dy, and when you take it with respect to y, it becomes a minus c plus dx. Sorry. All right, now you see that the Jacobian matrix will represent a local linear behavior of the type. So, x, let me abbreviate by putting a dot here, x dot y dot, this matrix or this vector will be this Jacobian matrix times x y. So, that is the local linearization, and the Jacobian matrix is this. So, obviously, we have to take a Jacobian matrix, or you have to locally linearize with respect to around, or locally linearize around a particular equilibrium point, and in this case we are not interested in the 0 0 equilibrium point, we are interested in this equilibrium point. So, in place of x y we have to put these values. Okay. So, let me put these values here, I clear some space. Now, a minus b y is 0, y is a minus b, y is a by b, a by b, cancels off, minus b x is c by d, dy d times y is a by b, and your minus c plus d, x is c by d, d cancels off, c cancels off, it gives 0. So, it is clear that the Jacobian matrix becomes very simple. These two terms are 0, 0 and 0, and these two terms have value, but instead of writing them directly, because then we have to write a lot, let me abbreviate this as minus p and this as say q. So, you just remember that minus p is nothing but minus p is just b c by d and q is a d by b. Okay. So, now the equation becomes x dot is equal to this Jacobian matrix times this, and you know that the solution of the differential equation in this region, which is given by say x dot is equal to say the Jacobian matrix times x, this is the equation. The solution of this equation depends on the eigenvalues of the matrix. This is something that you must have learnt in the first year. So, I am not going into the theory of why this should be so, but let us obtain the eigenvalues of this matrix. These are if you write the j minus lambda, lambda the eigenvalues, I is the identity matrix, this determinant should be equal to 0. Solution of this are the eigenvalues, know that. So, this becomes the determinant of 0 minus lambda, I has 1 here, minus p q, and this is 0 minus lambda. This is lambda square minus, and this product is minus p q equal to 0. So, lambda square plus p q equal to 0, and its solution is lambda is equal to this is lambda square is equal to minus p q, this gives lambda is equal to plus minus I square root of p q, and this is plus minus the imaginary number I square root of, now we can substitute your P was BC by D, BC by D, and your Q was AB, AD by B, AD by B, cancels off. So, is equal to plus minus I root over A C. So, notice that it has the eigenvalues have come to be purely imaginary numbers, and this is important. The eigenvalues being purely imaginary says that the oscillation in x should be a sinusoidal quantity, the oscillation in y should be another sinusoidal quantity, oscillation of y should be another sinusoidal quantity, but it would be 90° out of phase, and so on. So, this is x, this is y. And if you look at it in that x y space, these will be, let me clear off this so that you can clearly see the behavior in this plane. It will be going around, and depending on the initial condition, it will be just going around. That sort of explains why you always observe oscillations. It is because this character of the model, when we obtained the mathematical model, that enabled us to understand why there should be oscillation. It is because the eigenvalues come out to be purely imaginary. Had there been a real term here, then it would be either incoming or outgoing spiral behavior, depending on whether the real term is negative or positive, but in this case it has come to be a purely imaginary number. It also gives the insight that the eigenvalues are dependent only on this term and this term, A and C. So, how does the prey population increase if there were no predator population, or how does the predator population decrease if there is no prey population? These factors actually determine the eigenvalues. So, the rate at which it will oscillate, the frequency of that oscillation will depend on these two parameters. Now, you might ask, actually it was a very simplistic model, not really a realistic model. It was a very simplistic model. We sort of assumed things, and I have not really stated the assumptions, but you can easily see what the assumptions are. For example, we have made the assumption that in the absence of the predator population, the prey population will increase. It will be just dx dt is equal to Ax. So, let me just clear off some space. We have assumed that in the absence of predators, our dx dt will be only Ax. Now, before I go into that, after having obtained this model, the theorist will tell the observational biologists that go forth and check. my model says that it will oscillate, and it will oscillate with a frequency such and such. Frequencies will be related to the eigenvalues root over a by c. The eigenvalues will be root over a by c, and so go forth and check whether you are getting that or not. Or is the actual behavior deviating significantly from these elliptical orbits that the model predicts. So, these things again the observational biologists will check in the real life situation and will come back and tell where the inaccuracies were. And then the theorist will again have to go back to the equation and figure out where we had made some assumption that might be invalid. For example, one assumption was this. Now, if this is the equation, its solution is x of t is the initial x, say x naught, e to the power a t. So, it is actually a graph that continuously increases exponentially. So, this is the x, this is the time, this is the x. The graph this increases exponentially, but in a real life forest, if there is no tiger, can the number of deer increase to infinity values? No, that cannot happen, because there is limitation of the food in that forest, and so after some time it must sort of taper off something like this, and that can be incorporated if we say dx dt is a x is there, but there should be another term. If we add and multiply another term 1 minus x, then when x is large, then 1 minus x will be small, and naturally the rate of increase will again decay, will fall. As a result, it will give like a graph like this. So, the next logical improvement should be to place in place of a x something like this. So, similarly, you can imagine that there can be various improvements. In the predation term, we had put just a multiplication term, but that might not be a very good representation of the actual decay of the prey population due to predation, or actual increase of the predator population due to the availability of food. And so, the functional forms here might be more complicated, and people have proposed proper functional forms to take into account various possibilities. For example, in case of tigers, there has to be a period when the mother has to train the tiger cub to hunt, otherwise they cannot hunt. The hunting is a acquired character, it is not something that is innate of a tiger. So, one has to learn how to hunt, and that can be put into the model, and so on and so forth. You can also improve upon this. What I am trying to point out is that the way to produce a model is first, based on the first principles, produce a model, find out what its predictions would be, and then check those predictions against physical reality, and wherever the predictions differ from the actual physical reality, there you have to improve upon that model, incrementally trying to approximate physical reality as much as possible. So, that is the process of model building.